yes, it's a joint work with Mark Rudelson. And here's a problem that we care about. So we want to find the volume of a convex polyhedron. So the polyhedron is given by a system of linear equations and inequalities which are meant coordinate-wise, right? So the matrix A is like m by n matrix of the full rank, right? And so we get a picture of looking something like this, well, in dimension 2. And we assume that, of course, the polyhedron is bounded and has a non-empty relative interior. So we are computing the n minus m dimensional volume, right? And of course, so there are algorithms, right? Markov chain Monte Carlo algorithms that would do that. But so our goal here is to get as close to a formula, right, as possible, so that in particular, for example, we can get some idea for the volume of a polyhedron in a family of polyhedra, right? So that's the goal. So any objections to that? Okay, if not, so this is what we do. So we consider, so the non-formulaic sort of part of this formula is that we do have to solve a single optimization problem on this polyhedron. So we want to maximize the sum of logs of the coordinates, right? So it's a concave function, of course, so the maximum will be attained in a single point. So the reason I put n here is because then this function begins to look like entropy, and that's the topic of the conference, and that's how it appears. So it's an entropy, and I'm going to talk about it. But for the moment, just to introduce the formula, so we maximize this function, right, on the polyhedron, so the maximum is attained at a single point. And curiously, so it has a name, so it's, I think it's called the analytic center of the polyhedron, and it's at the source of the interior points method. So there was a very early, like 1988, I believe, paper of Jim Renegar, which sort of was at the source of interior point methods, and that was the sort of the chief object there, that the sum, the point that maximizes the sum of logs of the coordinates, right? So we compute this point, and from that point on, it becomes like a formula, so not just an algorithm. So here's a formula, right? So we still have this polyhedron defined by a system of linear equations, and the linear equations are independent, defined by coordinate-wise inequalities. So we already computed the analytic center. Now what we do, we take the matrix A, right, which looks like a rectangular matrix, and multiply the j's column, right, by the j's coordinate of that analytic center. And then what we do, we compute two determinants. So one is A times A transpose. So that would be M by M matrix, this one. And the other one, the same for the scaled matrix A, that is for matrix B. So that's two determinants. Then we take the ratio of square roots and multiply by e to the, that function f that we maximize, which is really e to the n times the product of the coordinates of the analytic center. And what we claim is that what we get is a number which is not hard to compute from the look of it. So which approximates the volume within a multiplicative factor. So gamma is an absolute constant. And I should also say that we don't know, I mean, if it's underestimate or overestimate always, probably not. But what's true is that the volume is not greater than some absolute constant greater than 1 raised to the codimension, right? And not smaller than some absolute constant less than 1 raised to the codimension times this estimate, right? And later on, I'll state an exact result where we actually took some pains to estimate this constant, okay? So, but so far, so this is the formula. This is how we estimate the volume, and the claim that we got a volume within a factor absolute constant to the m, where m is again the codimension, right? So m is this number, the number of equations, right? So any objections to that so far?
Can I ask a question?
Yeah, sure, go ahead.
So you took a standardization of the polytope where you took it to be defined by ax equals b and x bigger than or equal to 0. So I know that other polytopes can be transformed by linear transformation to this form, but then the volume, the n-1, sorry, the appropriate volume changes, right?
Well, but on the linear transformations, volume changes predictably, right? It gets multiplied. But if it's an honest linear transformation, it's not projective, then you just get the volume multiplied by the determinant, right?
But it's a lower dimensional volume, right?
Well, I mean, so suppose you have a polyhedron, right? Mm-hmm. Which is two-dimensional with 5 facets, right? So yes, you can represent it as what? As a two-dimensional section of a 5-dimensional portent, right?
Right.
And then the theorem says that you can estimate it within the absolute constant to the what? To the, so there are 3 equations, right? To the cube, right?
Oh, I see. Okay.
Yeah, so that's, well, of course, I mean, there's no free lunch, right? So we're not solving all the problems by formula, right? So there is always something we have to pay, right, here and there, right?
Yeah, thanks.
Okay.
Yeah.
Yeah, jolly good. So so one thing that I'd like to just draw attention to, that at least it scales correctly, right? So if we kind of dilate the polytope, right? So it's still here multiplied by a positive constant, then what happens? Then this center also gets scaled by that constant. So we get that constant to the n, but so this determinant doesn't change, but that gets smaller by that constant to the m. So in the end, we get the right scaling, right? So it's sort of a sanity check that it's not completely outrageous, right? To claim that this is volume. Well, up to that constant, right? So, and if there are no objections, I'd like to give more sort of reasons, more sort of sanity check talk here, right? So what happens if we are talking about the simplex? So if it's just one equation, so because things scale correctly, so we might as well assume that it's just one equation, the sum of the coordinates with some coefficients equal to n. And now, since we want to get a bounded polyhedron with non-empty interior, so the only possibility is that all the coefficients are actually positive. Then it's not very hard to compute the analytic center, and then that's the estimate we get. Let's get some expression. But on the other hand, we all know how to compute the volume of a simplex, and that's the exact formula, which looks kind of suspiciously close to the approximation, right? And in fact, if we sort of use Stirling's formula here, right, then what we have is that the volume is actually 1 over within a constant as promised. So I promised that it's constant to the number of equations. So here's one equation. So here's the constant 1 over square root of 2 pi. And furthermore, within that constant, it becomes sort of asymptotically, because of the Stirling's formula, asymptotically exact as the dimension grows, right? And that 1 over square root of 2 pi is not accidental. It will show up there several times, although probably not always, right? So, but before we go to that, so anything the matter here with the simplex? So it still goes.
I guess everything is equivariant to dilate in one coordinate also, so you can easily assume that all the AIs are the same.
Yes, of course,
matter.
right.
It's just kind of like, yeah, you just have to check the all one's direction, basically.
So, well, is that true? So it's is it a linear? It's projective transformation, right? It's
yeah, but I think like the 1 over zi cancel. Oh yeah, I didn't write. I mean, I guess I'm asking, is it true? I think
it's probably not, because it looks like a projective transformation to me, and therefore the projective transformation changes volume in some well, in some way, right? So you get some non-constant density.
I see. Okay.
Yeah. But anyhow, so
yeah, sorry, Sasha. Yeah, I have a question. So it feels like, given that you're talking about the analytic center, your volume is measuring a volume of some ball, like maybe some Daikin ellipsoid or something like that.
Well,
I'm wondering if there's.
Mm-hmm.
I'm sorry.
Yeah, go ahead.
I mean, the question is there some physical intuition of the quantity that you wrote down in an earlier slide as a proxy for the volume? Is it a volume of some ellipsoid associated to the body, or what is it?
Yeah, so I'll definitely get back to that. Right. I will not prove it, but I almost prove it, modulo some hand waving. But it's not an ellipsoid because it has the wrong dimension, right? So an ellipsoid and everything will be in all the dimension n minus m, right? It will have the dimension of the polytope itself, right? But here I claim that the constant to the codimension, right? So it lives in different space, sort of, in the complementary space. Okay.
Okay.
Yeah. Jolly good. So, right, where were we? Right. So here's another example, more interesting. So the polytope of doubly stochastic matrices, which is also known as Berger von Neumann polytope, right? It's a popular in combinatorics. So you consider the conditions all non-negative matrices, right? And you sum up, you say that the sum in every row and in every column should be 1. And here's another question. Well, let me ask you a question. How many linear equations do I have now? If I have R rows and R columns, then altogether I have how many?
2R minus 1.
2R, exactly right. Yeah, because they're linearly dependent, right? And so the dimension of this polyhedron is this, R minus 1 squared. Well, that's pretty clear. You can sort of prescribe almost whatever you want here, and then you'll append it by, you'll compute uniquely things here and there, right? So the nice thing about it is that by symmetry, the analytic center is pretty clear. It will have 1 over R, oops, sorry, 1 over R everywhere, right? And therefore, we don't even have to do anything. So we get this formula. And luckily for us, so Rod Canfield and Brendan McKay actually computed the exact asymptotic as this size of the matrix goes to infinity. And that's their formula. So as we see, so we do have that codimension 2R minus 1, and we do have square root of 2 pi, which previously appeared in the simplex, in the formula for the simplex, right? And here we have it again. And that's not a coincidence. And also what's not, what's interesting here, and we get this curious factor, the cubic root of E, right? So in a paper with John Hartigan in 2010, so we called this, oops, sorry, again. We call this quantity where we just divide by 2 pi to the m over 2, which worked in the case of a simplex and seems to work here, up to that cubic root of E, the Gaussian approximation. And we proved that it holds for some condition, when some conditions is satisfied, it holds, I mean, meaning that you get asymptotically exact formulas for families of polyhedron, right? So, and I'm also going to talk about this. So why did we call this, right? So that's another example. So any objections here? Right. So then let me give another example where we don't really know any formula, and we suspect that, I suspect that Gaussian doesn't work here. So that's a formula of what's called three-way planar transportation polydopes. So now you have cubes, cubic arrays, R by R by R, and you fill it with non-negative numbers such that the sum in every skewer is something like, well, it looks like a skewer, something that you can push through in every column, row, and whatever you call it, I prefer to call it skewer, is exactly 1. And again, the nice thing about the analytic center is that it's very easy to compute because by symmetry, all coordinates will have the same value, right? 1 over R. And the dimension here is R minus 1 cubed. That's again because the linear equations that you get like 3R squared linear equations, but they're not linearly dependent. And so we get this formula for the quantity that we care about, and this is it. And that's the best that we know. We don't know if anyone computed it more precisely. So it approximates, our general result says that it approximates, at least in the sort of logarithmic asymptotic, so up to a factor like constant to the R squared, right? Because the codimension is roughly like 3R squared or something, right? So, and that's the as exact as we can get here. So anything here? Okay, so now I'd like to actually state the main theorem. So the main theorem is, well, it's it just says that what I've been saying, that the number we compute approximates within some constant to the m, to the codimension. And so we got some constants, right? So the ratio is about 5, I think, slightly less than 5 to the m, right, between the lower and the upper bound. we actually can improve this a little bit, 0.14 to like 0.24, but that requires really heavy machinery like KLS of thin shell slicing conjecture, although we actually we don't need them in the full strength, we just need any non-trivial bound, like n to the 1/4, right? So in the slicing conjecture would give us that, right? But still, I mean, it's some heavy stuff. So, well, for me, right? So whereas this bound is actually elementary, and that bound is also elementary, so, sort of, right? So that's the theorem, and now I think I'm going to give the idea of why the formula is true, the idea of the proof. Okay. So again, anything the matter? Right, so here, how we do that. So we need standard exponential random variables. So that's random variable with standard exponential density. And here's a simple lemma from our paper with John Hartigan, like many years ago, like 2010. So what it says that pick independent standard exponential random variables, all right? Then compute that analytic center and use its coordinate to scale these independent exponentials. So what you get, well, you get some distribution in the positive orthant, right, in Rn plus. And the claim that this density, the density of this random vector is constant on every point of the subspace of the polyhedron. And it actually equals to that value, e to the negative sum of logs weighted by n additive factor. So which is e to the negative n divided by the product of the coordinates of the center. So again, so start with standard exponential, use the analytic center to weight those standard exponentials. So you get some distribution with density. So the density is constant at every point. And that's a simple exercise in Lagrange multipliers. So, but there is some reason why it actually works. So that's what I called here a deeper reason, that this is actually, this distribution is the distribution of the maximum entropy among all distributions supported on the positive orthant and with expectation in the affine subspace. And the moment you say that, you realize that it has to be constant on that subspace because the density, because if it's not, you can rearrange the density, sort of average it more so that the expectation still stays in the affine subspace, but because you average, the entropy will go up, right? So the one-dimensional corollary, not a corollary, the one-dimensional case of this result is that if you ask me, so what's the distribution of the maximum entropy supported on the net positive ray and with a given expectation, that will be an exponential distribution, right? If expectation is 1, that will be standard. Otherwise, you just scale it, right, by that required expectation, right? So, and in n-dimensional situation, so to get it constant on that subspace, you have to rescale it by, you have to take the standard exponential, scale it by these, by the analytic center, right? Here it is. And why are we doing that? That's because then it gives us immediate corollary. So that allows us to express the volume as some density of some random variable, which actually lives in Rm, which will appear then in the error estimate. So, so we have these columns of the matrix A, and then what we do, we consider the random variable, which is a linear combination of these columns with standard exponential random weights, but scaled by the analytic center, which is the same thing to say that we take the linear combination of the columns of the matrix B, but scaled with exponential random variables, standard exponential. And then the volume is actually, that's if the standard like change of coordinates computation is expressed entirely all the in terms of the density of this random variable. So this random variable, once again, so it's a linear combination of independent exponentials, right? So, and that follows from this simple lemma that if we rescale standard exponential by analytic center, then we get random vector with density constant on the polyhedron. Right. So anything the matter now? Okay. So one good thing about this random variable, although we have sort of very rough idea what it may look like, we know actually quite a lot. So first we know that the expectation of this random variable is that vector B. So what's that B? So remember that the equation is AX equal B. So here's other B's. That's probably not a very good notation, but still. So, and what we do here, we actually look at the value of the density at its expectation, which is not a bad thing. Second, that the covariance matrix of that random variable is that very same matrix that comes into play in the formula, that the B times B transpose, right? That's all very easy to check, of course. And so the punchline that this density is log concave. Because, well, it's the density of the sum of independent log concave random variables, right? So those x's are independent, we scale them by the analytic center, they're still independent. So what we get a formula for the volume, which is the only the part that we don't know much. Well, we know actually much about, but we don't know exactly, is some log concave density computed at its expectation, right? Okay. So let me again pause for the for objections here. Okay. Jolly good. So then we can actually do a bit more. We can notice that the formula that we are using looks at this ratio of these two determinants, and that there is some freedom. So when we say that it's a polyhedron given by equations AX equal B and non-negativity constraints, there is some freedom in choosing the matrix of linear equations, right? So we can define the same affine subspace, of course we change B as well, by different matrix. So we can multiply it on the, on the left, right, by M by M matrix W, and the subspace doesn't change, but that matrix B will change. And therefore we can change it so that we get the identity. And the formula, the ratio doesn't change, of course. So we might as well assume that in the very beginning, the equations that we had were such that B transposes the identity so that the random variable y here is isotropic, right? So we want now we want the density of a log concave random variable computed at its expectation and which is isotropic. And that's enough to get this constant to the m, right? And that's basically how we do that. So basically the proof of the lower bound for the volume. So where is this volume? So the volume, to get the lower bound, we only use that. This is the density of the log concave isotropic random variable computed at its expectation. So we get an exponential lower bound, which is quite standard. So the proof of the upper bound is not, yeah, so apparently there is a typo here, it's really T, lowercase. So the proof of the upper bound uses the characteristic formula, characteristic function of that random variable, and then we basically kind of follow the proof of Keith's ball in his papers regarding the maximum possible volume of a section of a unit cube. Only our characteristic function looks simpler and the proof is simpler. So, but we pretty much mimic what Ball did to get an upper bound. So
what is the density for the simplex?
I'm sorry, what?
What's this Py for the simplex?
Oh, for the simplex, so you have just one equation. So it should be just exponential, right? So it's a linear combination of one. So it's right. So it should be exponential, right? Oh no, I'm sorry.
No. I mean,
no, I'm wrong.
It's untruncated exponential. Is that right?
No, it's so these are, or A's are, yeah. So it's gamma, right? It's gamma because it's sum of independent exponential. Well, maybe with different, maybe not gamma. It's the sum of one-dimensional independent exponentials, right? Scaled, so not necessarily standard. So for
so what is the support of this? What's the support of Y?
The support is non-negative.
The whole of negative
ortant, right?
Okay.
No negative line. No negative line. Sorry. Support is no negative line. So yeah, that's I never thought about it. Let's go back to this example. Where is that? Right. So we have we have n independent exponentials, right? One dimensional. We scale them by those z's, right? And add. And we get a one-dimensional thing, right? By the way, if all a's are equal, so we do get gamma, right? If they're not big, we get something, right? Which is supported on the positive ray, right? Log concave.
So
that makes sense.
You can probably find, I mean, there are some conditions under which this thing satisfies the central limit theorem, essentially.
That's what I'm going to talk about.
Definitely.
But yeah, that's what I'm going to talk about. Given that, yeah, I still have some time. How much exactly? So,
a bit, I mean, 9-10 minutes. Yeah.
9-10. Yeah, that would be enough. Right. That's exactly right. So where we were. Yeah. So we were here, right? So we proved the theorem, right? So the ultimate reason this works, because we are talking about the density of log concave function isotropic in the NS expectation. So if no other objections, so I would move to the central limit theorem. Other? Okay, jolly good. So here's the Gaussian formula that I mentioned several minutes ago. So we have this formula that the volume is expressed as in terms of the density of a random variable, which is sum of independent random variables, and the density is measured in its expectation. So it seems very tempting to say that it's probably Gaussian, right? Because, or close to Gaussian, because we adding many independent random variables. So, and if they kind of reasonably scaled with respect to each other, then we get close to Gaussian. And so we get this formula for the volume. And indeed, in the paper with John Hartigan 10 years ago, we showed that this formula holds asymptotically for various classes of polyhedron. But there is this interesting issue that for going back to, sorry, it may blur on your screen, going back to the polytope of doubly stochastic matrices. So look at that, right? So that e to the 1/3, which doesn't belong to a central limit theorem, but in fact, it turns out to belong to it, meaning that it's what is called the Edgeworth correction to the central limit theorem. So it's what you get in the central limit theorem, the correction, if your third and fourth moment sort of become a little unwidely there. So then you can still fix it by introducing that Edgeworth correction, and that's what happens there. That it's almost a central limit theorem, but not quite. So you have to push it by a constant factor there. Okay. So that thing with entropy seems to work fine, like for some extent. So in other situations, so although we cannot, of course, rely in discrete case, we cannot rely on this log concavity property that's so crucial. So suppose that we want to count just not the volume, but integer points in the same polyhedron, right? Then it's kind of scarier because we're certainly up against an sharp p-hard problem. We don't even know if there is one, but let's try to do this, to pull the same thing. So instead of that function f that was the sum of logs, we consider this function, which looks like this. So it's still concave, and it's actually entropy. So it's the maximum entropy of probability distribution on non-negative integers with a given expectation, right? So, and this distribution is necessarily geometric. And we can pull the same thing. So we can compute this discrete analytic center that maximizes that sum of these functions. And then the claim, again, from our paper with John Hartigan, is that now if we have vector of independent geometric random variables with those expectations, then the probability mass function is constant on all integer points and equal to that e to the negative entropy. And again, that's as such is an easy exercise in Lagrange multipliers. But that gives us something. So, right, so that's the justification of it. So basically we are looking again of the distribution of the maximum entropy among all supported on non-negative integers and with expectation and given a affine subspace. And then we can pull the same trick again, except that we don't have this mighty machinery of log concave functions, but we can still kind of hope for central limit theorem. So we introduce a random variable, which is the sum of independent random variables weighted by the columns, and we can express the number of integer points as in terms of the probability that this discrete random variable hits its expectation. And then we can just hope that maybe, just maybe, nothing else seems to work, maybe the central limit theorem works. And assuming that it kind of works, we get a bound, right? And we can pull the same trick with counting 0, 1 points, we get another bound. And I'd like to finish with 2 examples that sort of illustrates the numerics, because numbers do not lie. So this was computed by Jesus de la Era. So the number of 4 by 4 non-negative integer matrices with such row sums and such column sums was computed exactly by Diaconis and Efron in 1985. So it's this number, right? And the approximation we get is off by 6%. So, and what do we use here? So with our random variable is a sum of 16 independent 7-dimensional vectors, right? Discrete. And we apply central limit theorem and we get 6% off, which I thought wasn't bad. But then here's another example. So this time we have cubic arrays, 3 by 3 by 3, so 27 cubes altogether with slice sums. So these are sums not over skewers, but slices by planes. And here they are. And the exact number, again, computed by Jesus is that. And then the value, this Gaussian formula gives you the error like 0.2%. It's much better. And the reason it's much better is because we use the central limit theorem to approximate by Gaussian the sum of 27 independent 7 vectors, right? As opposed to 16. So we get closer to the Gaussian, we get a better error, right? And that's pretty much it. Yeah. Thank you very much.